Some harder limits now are ones that you can't really just sort of plug in the value. And a lot of times they aren't actually much harder, especially if you know what to do. So if you wanted to look at this limit as x approaches 4 of x squared minus 9 over x minus 3. Well, in this case, what happens when you plug in 4? Well, you get 4 squared minus 9 is 16 over 4 minus 3, which is just 1. So it equals 16. And everything seems pretty fine there. But now if we looked at the limit as x goes to 3 of x squared minus 9 over x minus 3, we don't really get something too nice because, let's see, 3 squared minus 9 is 0, 3 minus 3 is also 0. Well, what else can we do here? So let's look at this function x squared minus 9 over x minus 3. Well, this top part looks like something that we can factor. In fact, we can actually factor this down to x minus 3, x plus 3. And then this bottom part is still x minus 3. And again, we're still finding the limit as x goes to 3. Wow, that was a lot of 3's there. But let's see, this part is the same as this part everywhere except for x equals 3. At x equals 3, it's not really defined, but everywhere else, it's just going to be 1. And because of the nature of limits, we never actually hit this number 3. We never actually hit what we're getting the limit towards because we're just getting closer and closer to it. Thinking about that term of sequential limits, getting closer and closer to 3, but not actually needing to get there, we can actually just cancel these two terms out. So then we now have the limit as x goes to 3 of just x plus 3. And now we can plug in 3 here, and that just equals 6. Another way to use this is that, again, if we're going to look at something like the limit as x goes to 2 of x squared plus x minus 6 all over x minus 2. Well, again, when you plug in 2, you're going to get 0 over 0. But we can factor this again, and we're left with limit as x goes to 2 of x minus 2 times x plus 3 over x minus 2. X is never actually equal to 2 when dealing with this sort of sequence that approaches 2. So now this is just plugging 2 into x plus 3, and we get 5. So all this works out a lot better now. We just have to think about factoring. But now what happens if we have something a little bit harder, where we have the limit as x goes to 4 of square root of x minus 2 over x minus 4. So we can sort of think about this in a factoring sense. We actually can factor x minus 4 into square root of x minus 2 and square root of x plus 2. But just because this could come up in another, maybe more difficult way that doesn't have as easy of a way to factor it, let's multiply by a tricky form of 1. So something that might seem kind of arbitrary, might seem kind of, where's this coming from, and am I just doing this because I have seen something like this before and I just know that this is going to be the right thing to do? Well, yeah, that a lot of times that's kind of how it works in mathematics. One of my high school teachers actually taught me about this sort of term that I think actually his teacher coined, where in this, it's kind of relating to, well, Mario. You have this game where you're trying to do a lot, but one of the things that you can achieve is finding coins by sort of just punching the bricks. But occasionally you'll just be running kind of in the middle of nowhere, punch something random, and there's this invisible brick there that will give you a coin or whatever you're looking for. And you think, how did somebody know to find that? Well, somebody was just doing a bunch of random stuff maybe and found it by luck, and then they told other people, and that knowledge spread around, And eventually, somebody knew to find it because they just sort of knew where it was. They knew what to do. So in this way, because I've seen these types of problems before, and I was taught to do this by someone else who was probably taught to do this by someone else who was taught to do this by somebody who then just was really smart and figured this out, well, you end up having this sort of invisible brick where you multiply by a fancy form of 1. What it does is it, in a way, gets rid of this square root, and it's actually going to turn it into this number here, or this little function here. So let's go ahead and expand this to kind of make that a little bit more clear and get away from Mario, I guess. So square root of x times square root of x is just x. Square root of x times 2 is 2x, but minus 2 times square root of x, those cancel out. And then you have negative 2 times 2 is just 4. And then on the bottom, I'm going to leave these alone, and we're just going to have x minus 4 times square root of x plus 2. Again, we never really have x equals 4, so we can cancel this out. And now we can just plug in 4, so you have 1 divided by square root of 4, which is 2, plus 2, and the limit is 1/4. Okay, so now I'm going to erase the board, and I'm going to get into another example that you can't really manipulate too much using just algebra. So this limit here is one that comes up pretty often, actually, and it's kind of a limit that everyone ends up studying at some point. Everyone ends up looking at. And just like that last limit, there is going to be this sort of invisible brick method that we want to utilize to be able to figure this out. So algebraically, we can't really do anything here. You can't factor anything. You can't just divide x on, you can't multiply by some fancy form of 1. You can't get rid of this x really, and no matter what, you're kind of left with this 0 over 0 case. However, and again, this was not, I didn't come up with this. I don't think I ever really would have been able to, but some smart person figured out that you can solve it this way, and now it makes this much easier to figure out. So if we come up with this, if we look back at the unit circle here, we can sort of draw 3 shapes coming out of here. We can, well, first let's go ahead and create our angle x. So if this angle right here is x, and it's just made by drawing some line on the unit circle and connecting there, then we can draw 3 shapes. First, let's connect the top point here to this point 1, 0, where the circle intersects this x-axis. Well, the height here is going to be sine of x. So let's draw this in orange, and let's just sort of bring in here saying that this is sine of x. Okay, so now we have this sort of smaller triangle. Now, in purple, let's draw in this, this slice of the circle here, the sector, and this is another area that we're going to want to find. And then finally, let's extend this line so that it comes up and out, and then we'll draw it just long enough so that we have a line that's tangent to the circle right here, right at this 1x, or 1, 0 point. So now we have 3 shapes. We have this blue triangle, we have this purple sector, and we have this green triangle. And we can see that this blue triangle is always going to be strictly less than or equal to this purple sector, because there's this extra little area right here, which is always going to be less than or equal to this bigger green triangle. And now this is starting to look like squeeze theorem, which we actually talked about in the last video, because you have this sort of lower bound, upper bound, and this thing that you always want, and this thing in the middle. But why does this necessarily relate to squeeze theorem is because, well, let's go ahead and figure out what the areas are of each thing, and I think it'll become a little bit more apparent. So the area of this blue triangle, well, the base is just always 1, because that's what the radius of the unit circle is, and the height is sine of x. So we have sine of x times 1 divided by 2. So it's just sine of x over 2. Now, what is the area of this sector? Well, the total area of the circle is pi, and the angle x in relation to like how much the circle is taken up is a ratio of that, in the sense that the ratio that the angle x takes up of the whole circle is x over 2 pi, because there's 2 pi radians in the full circle, and then we're just multiplying that by pi, canceling that out, and we get that this area of the sector is always x over 2. And that's always less than, well, what about this bigger triangle? Well, we have the base is 1, and what's this height here? Well, let's see, it looks like this smaller triangle right here is going to be similar to this bigger triangle because it has the same angle, and it has, it's hard to see that these two angles are also going to be the same because this is 90 degrees on both sides, so 90 minus x is going to be the same there. So these are similar triangles, and this height over this height is sine over cosine, and this height is something over 1. So it's sine over cosine over 1, or tangent. And then we also have to divide it by 2. So I'm going to go ahead and actually write this as sine of x over 2 cosine of x. So now we can get rid of all these 2's because we're just going to multiply by 2 on each side, and then we're going to divide by sine of x. So now we have 1 is going to be less than or equal to x over sine of x, which is going to be less than or equal to 1 over cosine of x. And then we can take the reciprocal of every side, and that will flip these inequalities. So now we have cosine of x is always going to be less than or equal to sine of x over x, which is less than or equal to 1. And now it might seem a little bit more apparent where this idea of squeeze theorem is coming from, because the limit of 1 going to 0, but really going anywhere, is just 1. So if we take the limit everywhere, well, the limit of 1 as x goes to 0 is just going to be 1. And the limit as x goes to 0 of cosine of x is also 1. So that means that the limit of sine of x over x has to be in between these two. So now we have that 1 is in between the limit as x goes to 0 of sine of x over x, which is also less than or equal to 1. So it's in between these two values of 1, which means that the limit as x goes to 0 of sine of x over x must equal 1.